Hi, I'm Fernando Pereira from UFMG Brazil, and today we talk about how to split live ranges to ensure that a given data flow analysis has the single information property. To motivate this class, we shall see 4 examples of different static analysis, and we will see how we can make them sparse. Let's start inferring virtual tables for dynamic typed languages. Dynamic languages like Lua, Python, and JavaScript represent objects as hash tables. It's possible to speed up computations in these languages if we replace these hash tables with virtual tables, which are tables with a fixed layout pointing to the attributes and methods of a class. But to implement this optimization, we need to discover all the methods that belong to an object at different points of existence during the execution of a program. We shall use this program on the right to explain how the analysis works. We discover the type of an object, that is, the methods that belong to it, based on how that object is used. Whenever a method is invoked on an object, we know that the object must have that method, at least in the program point immediately before the invocation happened. We are, of course, simplifying the analysis, but an important question is, why does information propagate backwardly? Or, why can't we simply assume that the method remains in the object after it's used? Would you like to think about this question? The things that in these dynamic languages that represent objects as hash tables, we can do anything inside the method that has been just invoked. We could even remove the method itself, like in the example where we assign 0 to the method m inside m itself in a Python class. So, for now, we assume that it's safe to propagate information backwardly. For our example, we have these dataflow facts flowing across the program. Each color represents a different dataflow fact. New facts arise when we invoke methods or when we instantiate objects. To add the single information property to the analysis, we need to split live ranges whenever methods are invoked onto objects. And we need to join information at the points where information collides. In the case of this example, these are the branches, as multiple dataflow facts might arrive at the different paths that stem from the branch. We can see the new variable names in this figure. Notice that when we split live range due to information colliding backwardly, we use a special kind of instruction called a sigma function. Sigma functions are similar to phi functions, as we will see later. The only difference between them is the direction in which they merge information. Phi functions merge information that propagates forwardly, and sigma functions merge information that propagates backwardly. And given these names, we can create a constraint system to represent the data flow analysis. Can you take a look into these constraints? Try to make sure that you understand the meaning of them. Each constraint takes information on the left side and creates information on the right side. In this program, we have used SSA form. However, SSA form is not really necessary for this analysis to work. New information does not appear at join points, thus we do not need phi functions. Indeed, the transfer functions associated with the phi functions are trivial. However, using SSA forms is still good, for a number of reasons. First of all, it's already default in most compilers. Second, SSA form simplifies some supporting analysis like liveness, for instance, in the implementation of compilers. You can see our example in SSA form on the left, and in non-SSA form on the right. Let's take a look into the constraint system of the program on the right. Would you like to pick up a piece of paper and try to write these constraints before we move on to the next slide? Here they are. As you can see, we have less constraints, and none of them is trivial. If you go back to the constraints of the SSA form program, you will see that we had a few trivial constraints associated with the phi functions. Let's now consider another analysis. This time we shall talk about tainted flow analysis. Could you stop the video and read the comic strip for some motivation? We shall apply this analysis on the program on the right. The goal is to know if some input that an adversary can control might reach any sensitive site within the program. Information appears whenever variables are defined. For instance, if a variable is defined via an assignment from input, then we know that it's tainted. On the other hand, if a variable is defined with a constant, then it cannot be tainted. And we have conditional tests that check if a variable is tainted or clean. So where should we split live range? To ensure the single information property, we must split live range at definition points and after branches. Branches that check the state of a variable are called sanitizers, and they generate new information. Information propagates forwardly, so it collides at join points. And we need to split variables at those points too. We do it using 5 functions. And once we are done with the live range splitting, we can build constraints. These are the constraints that we use to solve tainted flow analysis. Can you solve them to see if we have any tainted variable arriving at some echo instruction? Let's now move on to a third analysis that will help us to show how sparse analysis work. Type-safe languages usually check if an object is null before invoking a method onto that object. We can remove some of these tests with static analysis. For instance, for this program on the right, which call will never be null? The call to m at L3 cannot be null, because the same method has been called before at L2. On the other hand, the call of m at L4 could be null. Just imagine that function foo returns a null object. So in this case, can you think about a static analysis to find objects that could be null? How does information propagate? And how does information meet? New information appears after uses of objects, or in other words, after we invoke methods onto these objects. And this information propagates forwardly. Contrary to our first example in Python, this time we are working with a statically typed language like Java that has immutable classes. Anyways, and we can join information at 5 functions. Here you can see the constraints that we can derive from this program after live range splitting. We have not talked about it, but how's the meat of this analysis? What happens once an object that could be null meets another object that can never be null? That's the same as asking what is the state of v4 in this program. Could it be null? This last question I will not answer. If you want an answer, you can ask in the comments, and we can discuss it over there. In the next class, we start talking about live range splitting strategies and how to implement them. Thank you.